Good afternoon everybody and welcome to today's worked exam answer video. Today I'm having a look at a AS/Year 12 content based multiple choice question whereby we're having a look at the reactions of a halogenoalkane, thinking about which products we can get in the reaction with potassium hydroxide and which product from that list there, which product we cannot get in this particular type of reaction. So this will come up in the halogenoalkanes topic in the Year 12 part of the A-level content. So if you're in Year 13, you will also need to be able to do this. Now, this also links in a little bit to thinking about organic synthesis, in the sense that we need to be able to very quickly recognise different homologous series, be able to identify reagents that we've got, and kind of be able to picture, okay, if I'm starting with a halogenoalkane, what different products can I make? We can make alkenes, we can make alcohols, we can make nitriles, and we can make primary amines. And then those primary amines can carry on reacting all the way to a quaternary ammonium salt. There's quite a lot of things that halogenoalkanes can do. Now, in this particular question, we are focusing on potassium hydroxide. So we are thinking specifically about hydroxide ions here. So we're not going to be thinking about ammonia as a nucleophile. We're not thinking about the cyanide ion as a nucleophile. We're thinking about OH minus ions and what they can act as. And one of those is a nucleophile, but it can also act as a base, and that's why we can get both an alcohol product here and also some alkene products. Now, based on the four options that we've got, we can see that only one of those products is an alcohol. So that is essentially what they're suggesting is the product of nucleophilic substitution. And in nucleophilic substitution, the OH will be acting as a nucleophile. It will attack the carbon, which is bonded to the bromine in this case, or whatever the halogen is, and then the bromine will get swapped off and the OH will go in its place. Now, we might not have to draw that on, we might be able to visualise that that's what's going to happen, and in the fullness of time that would be my hope, that you can kind of picture, okay, nucleophilic substitution, the OH will end up where the Br is. Is that what we've got in this product A? Yes, it is. Now the question is asking us which is not a possible product, so that will be formed, and therefore A is not the answer that we're looking for. Now, we can only ever get one nucleophilic substitution product because the nucleophile, the hydroxide ion in this case, will always be attacking the carbon with the halogen atom attached to it. So they're always going to swap places, nothing else is going to get swapped, etc. Okay. Now, the other reaction that we can get is we can get elimination happening. And in elimination, we've got OH minus ions, which are acting not as a nucleophile anymore, but as a base. And a base is a proton acceptor. So what the OH minus ions are going to do here is they are going to take a hydrogen from a neighbouring carbon. Those electrons in that carbon-hydrogen bond will then give us our double bond, and then the bromine will be eliminated. So for example, if I were to draw the hydrogen atom on there, because it is there, this is a skeletal representation, so don't let that catch you out either. There will be two hydrogens on that carbon there. So the OH would then come in and take that hydrogen as a proton, so it won't leave with any of its own electrons. That will then give us water as a product. Then the electrons in the carbon-hydrogen bond will give us the double bond, and then the bromine will get kicked out. Now again, I'm not suggesting that we're going to have to draw this mechanism, or we should be drawing this mechanism. My hope would be that you know the mechanism well enough to be able to picture, yes, if I take a hydrogen from there, the double bond will go here. So that option D is a product that we get via elimination. So D is viable, so not the answer we're looking for here. When we're thinking about elimination, we do have the possibility for there to be multiple different alkene products formed, and that's because if the carbon that has the halogen atom on it has a carbon either side, and we can take a hydrogen from either side, and it's an asymmetrical molecule, then we'll get different position isomers being made. So I could also look to take a hydrogen that's on there, and even though there's a methyl group on that carbon, there's still space for a hydrogen. So if my OH then was to take that proton, or take that hydrogen that leaves with no electrons, then we'd go from the carbon-hydrogen bond, the electrons would go to give us a double bond, and then again, the bromine would be eliminated. So that means the double bond is going to go between the carbon that had the bromine and the carbon with the methyl, which is option C. Therefore, by process of elimination, we've worked out that the product we can't form is B, which if we look at where the position of the bromine is, and we think about how we would get the double bond to be formed there, we would need to get rid of a hydrogen either from it'd have to either be from the end of the methyl group to then put the double bond there, but then we wouldn't be able to kick out the bromine because we'd be thinking about sort of a carbon atom too far away, if you see what I mean, from where the bromine is. So yeah, that's just not going to work, or we'd have to take a hydrogen from that hydrogen, but then have the double bond going that way, which again is not going to enable us to eliminate the bromine. So B is not a possible product there, and the way in which to work that out is to think about what our substitution product would be, and then what our elimination products will be. And obviously if it's a multiple choice question, there has to be 3 correct options, and if only one's going to come from nucleophilic substitution, the other 2 correct options should be alkenes coming from elimination. So you're basically here trying to work out, if you know the substitution product is right, which of those 3 alkenes is wrong. So yeah, from an organic synthesis point of view, we do need to be able to kind of think very quickly, oh, halogenoalkane, what reactions can that undergo, and have them very accessible in the brain, which is going to take a lot of practice. It's exactly the same reactions as you will have seen in year 12, it's just now that you've learned a lot more of them, it's harder to potentially remember all of them individually at this stage, but it's also about making those connections from one homologous series to another. Hopefully that's been helpful, guys. Any questions, as always, please let me know, and thank you so much for watching.